Just like terminology is very important in physics, notation, or how we write our variables, is also extremely important in physics. What we're doing in physics when we're writing things down is communicating either to ourselves or somebody else or a future self. So it's really important that we're clear so when we come back later to our problem or show our work to somebody else, we can understand what it is we've done and what our thought process was. So particularly when you're learning about forces, it's really important to have a clear labeling convention so you know what type of force we are looking at, and then the object that is exerting the force and the object that is acted on by the force. So we call the object that exerts the force the agent of the force, and then we often call the thing that is experiencing the force the object of the force. So forces are vectors, so we always know that whenever we write a force vector, we should have an arrow on top of it, like this. In this class, we always use the word F to show that something is a force, as compared to an acceleration or a velocity, as just a way to be very clear when we're writing equations and drawing free body diagrams that the things that are on that diagram are indeed forces. You'll see other conventions in other places, but this is the convention we use in this class. So we label all forces with a capital F to show that it's a force. Second, we use a subscript to denote which type of force it is. So that could be a normal force, like this. It could be a gravitational force with an F sub g. Or another example is a frictional force, F sub F. Now we also want to be sure to label what is the agent and what is the object of the force. So the agent, the thing that acts, so for example, if we have a block that's sliding on a table, then if we're talking about the force of the table on the block, we might write it like this: F normal force of the table on the block. The frictional force, we might also talk about the frictional force that the table exerts on the block. We could also write a different force, the frictional force that the block exerts on the table, which we'll talk next week about how those two are related to one another. And when we talk about the force of gravity, we want to talk about what the force of gravity is acting on. So we could be talking about the force of gravity, for example, on the block. Now, often we don't specify this when we write the force of gravity because usually the thing acting on the force, the thing causing the force is the Earth. So if we wanted to be very proper, we would say the force of gravity, the Earth on the block. But we often leave off this Earth on because it's the norm, and we are just talking about, we just label the block. Right, we encourage you to use this convention because there may be problems where there are multiple normal forces. For example, let's say you have two blocks that are stacked on top of each other, block B and block A. If you just label your normal force as F sub n, it's not going to be clear to you if you're talking about the normal force exerted by block B on block A, by block A on block B, by block B on the table, by the table on block B. So that's why we really encourage you, especially as you're first learning, to be very careful to use this convention because having bad notation or unclear notation is often a reason that you'll get problems wrong on an exam, and we definitely don't want that to happen if we can avoid it. Okay, the last thing we'll discuss is conventions for drawing free body diagrams. So when we draw a free body diagram, also called a force diagram, here's what we do. We always start by choosing a single object to analyze. Because what we're doing when we're drawing a free body diagram is we're going to try and figure out what are all the forces on a particular object, and then we use that information to figure out what the corresponding motion of the object will be. So we choose a single object to analyze, and then we draw a large dot or a box, either way, to represent the object. And then what we do is we draw one vector to represent each force that acts on the object. So our free body diagram always only includes forces on the object. And this is because we're looking at everything that exerts a force on the object is going to determine how the object moves. The forces that are exerted by the object are things the object is doing to the outside world, not things that are causing it directly to move. So we only put forces on the free body diagram that are forces on the object. And what we then do is for all these forces, we place the tail of the force vector in the center of our free body diagram object. So for example, if we have some force, say it's a contact force caused by a hand, that might look like that. If we have a frictional force that is going this way, let's say it's caused by a table, that might look like this. So this would be the table on the object. This would be the hand on the object. We have the force of gravity, always if we're on the earth, on the object. And maybe we have some normal force of, say, a table. Maybe the object is sitting on a table, on the object. So we always draw these force diagrams where the tail of the vector is in the center, even if you have a cable where the object, say, is a block, and let's say you have a hand that's pushing on the block like this. When you draw the free body diagram, you might be tempted to do something like this and draw the force of the hand, the contact force of the hand on the block. But that can get really confusing if you draw some arrows this way, some arrows that way. It's much easier and clearer for people who are used to looking at the free body diagrams when all of the arrows start at the center. And then the last thing to do when you're drawing a free body diagram is double check that you have all the contact and the field forces. So the field forces, again in this class, the only one we'll talk about is gravity. All of the contact forces, you just want to look and see what's touching the object at the moment, and have I accounted for every kind of force that that thing touching the object could exert.